Now we're going to cover controls. On the air-fuel ratio controllers, people wonder why you need them. The engine will run fine without them, but why do you need one? Okay. Some of the new stuff that's out, this is a EIM display. This would connect to your AFR. We build the entire panels as well. Air-fuel ratio controller consists of a display, and you have an advanced version and you have a light version. Okay, why do you need an air-fuel ratio controller? The main purpose of an AFR is to maintain the oxygen content of the exhaust at a level suitable for the maximum performance of the catalyst element. Without an AFR, the engine will not maintain the oxygen content through load changes, fuel changes, and ambient changes. Okay. This is a chart that's showing us what reaction takes place using a catalytic converter and an air-fuel ratio controller. The top sheet, the top graph, is just strictly what's going on with an engine without a catalytic converter in it. So earlier we spoke of lambda. Here's a lambda 1, the perfect burn. Okay, so if we're at this perfect burn and we're on a rich burn engine, we know that our NOx is greatest as we're just a little bit lean of stoichiometry. So this line is representing our NOx. Okay, this blue line is representing our NOx, and this line is representing our oxygen. Okay, so we're leaning the engine out, the oxygen is increasing, and we're going to reach this point where we're producing the highest NOx, is also usually where the best performance is on a rich burn engine. Now here's what happens to those same emissions with a catalytic converter. As they pass through the catalyst and our engine's running correctly, we're at a lambda about 0.97 here. That's an optimum for most catalyst elements. You'll see a huge reduction in the numbers. Okay, so you'll see the emissions are much, much lower coming through the catalyst. This is when everything is working perfectly. Our NOx has literally been taken down to nothing. Our CO is below this line. It's hanging down here right with the NOx. And you can see some of our other unburned hydrocarbons don't reduce quite as well, but they're certainly reducing by quite a bit. We're at least getting the 40% reduction. Okay. Now the differences in the air-fuel ratio controllers, the AFRC Advanced or the AFRC LITE interfaces directly with sensors and the valves, so the oxygen sensors, the thermocouples, and the digital power valves. It handles all computation for control. In other words, you don't have to choose a set point with the AFRC Advanced. You have the option to use it as a set point control, or you can use it as an auto control mode. Inputs, you have to have O2 sensors, 2 of them for the AFRC Advanced, 1 pre-catalyst, 1 post-catalyst. Thermocouples, you're going to run pre and post thermocouples, pre and post catalyst thermocouples, excuse me. Optional inputs, optional sensors, you can run a thermistor just for ambient temperature, intake manifold temperature, whatever you'd like. You have a general purpose analog input. If you want to hook an analog input and set it up, you want to use anything from suction pressure on your compressor to manifold pressure. There's several different things you can use. There's a mag pickup you can use for an engine run signal. You can use a separate manifold pressure. There's an input strictly for manifold pressure. And our outputs on this are going to be the digital power valves. We call them a DPV. And the alarm shutdown relay, that's just an output that shunts to ground. Should you put this in a panel other than an EMIT panel, you can tie it to their annunciator and shut the unit down. They're Class 1 Div 2 certified. The EIM, this is the display. It's 8-inch touchscreen, provides user with an interface and system interaction. It's Modbus RTU through a RS-485 port. Data logging files are able to download through the USB port. That's a great feature of this. We can handle up to 32 days of data is always being recorded in this. So it's continually data logging all the inputs and all the outputs on this as well. Support multiple control modules with one user interface. So by that it means we can run an AFR, we can run a governor, we can run an enunciator, we can run ignition. All of those can be tied together at the same time using one module, or any one of those modules can be used with this display independently. Okay. It has 3 different security access modes. If you're in operator mode, you can't make any changes, you can only view. Then there's a mode for setup, and there's a mode for engineering. And again, this one is class 1 div 2 certified. Okay. This is what your typical kit is going to look like if you're just doing a standard air-fuel ratio control kit. Okay. You're going to have the display. You're going to have the module, whether it's an AFRC Advanced or an AFRC LITE. You're going to have a harness for the O2 sensors. If you've got 2 O2 sensors, you're going to run 2 harnesses. If you've got a single bank or a dual bank, you're going to run a harness for each stepper motor that you have or digital power valve. And then you're going to have the required oxygen sensors pre and post, and the thermocouples pre and post. Okay, and this one is just a power supply harness in the picture. Okay, this is what the back of the display looks like. You have a USB port, you got your Modbus RTU terminals, and you've got your CAN bus, and you've got your power and your ground, and you have an on-off switch. You also have a little switch right here called a CAN termination switch. This is used in an open or closed mode depending upon where this falls in the system for the CAN bus. Typically the display is in an on position or closed. Okay, the AFRC Advanced Anatomy. Again, you have your CAN bus. That's how the units are going to talk to the display and talk to each other. You have your CAN termination switch. Your auxiliary inputs. You've got your map sensors, your ambient temperatures. You've got both a left and a right map, and a power supply for your analog inputs. Here's an optional analog input. You have an oil pressure, and you have a tachometer input here as well. Then you have a left bank, or if you're only using single, one bank, you would tie in right here for your digital power valve. If you're using 2, you would have a left and a right digital power valve hooked up. On-off switch, power good. That means you've got 12 to 30 volts. If you don't have that, that light won't be good. You'll have power fault. Okay. You have a USB. We use that USB port for software updates. Was a primary purpose, and then the other feature with that is we can also do instantaneous data logging at a much tighter increment than through the display. So if a guy was troubleshooting, you can pull the data off of that and send it in to us, and the engineers at EMIT can review that data and tell you exactly what's happening and what adjustments or what improvements you can make to that unit. And then you have O2 sensor inputs. The AFRC Advanced will support both a wideband and narrowband left bank and right bank and post-catalyst O2 sensors. Post-catalyst is always going to be a narrowband. Okay? And then we can support 3 type K thermocouples as well, typically pre-cat, post-cat, and manifold temperature. This control also has the ability for single set point control. It has the ability for mapped control, a custom built map, or you have the ability to run in auto control where you only determine whether you want it richer or leaner, and it tracks throughout all the loads. AFRC LITE, single bank is what you have. Here's your O2 sensor, here's your thermocouples, same, but you're missing the option to do dual bank with it. Everything else is the same. We spoke of the CAN bus system earlier. So we use a daisy chain if you're going to tie multiple modules together. By multiple modules, I mean if you're using an AFR, an enunciator, an EDT, or an ignition module or a governor module, they all tie together through the CAN high and CAN low and CAN common terminals. And they all talk to each other, they share each other's information, and they display it on the screen itself through the CAN bus system. Okay, typical wiring for an AFRC Advanced. Again, you have your power and your CAN wire. This goes to there. It's all that's going to be between the two modules. And then this one is going to have your left bank, right bank, and post-catalyst O2 sensor. Again, this Advanced will support wideband or narrowband sensors for the pre-catalyst. And this is where your stepper motor is going to tie in. And this is your thermocouple. As you can see, extremely simple to set up, extremely simple to wire and install. In a matter of hours, this system can be installed. Okay, single bank, typically used for your smaller horsepower single bank engine, one carburetor, one exhaust, but also the same control used on a 3516 Caterpillar. Therefore, single bank meaning one carburetor and one exhaust outlet. Okay, so you got one O2 sensor pre-catalyst, one O2 sensor post-catalyst, and your thermocouples, and one fuel control valve or digital power valve is what we refer to them as. And AFRC LITE, this one supports only a narrowband sensor and no post-catalyst O2 sensor, and is single set point control or mapping only. Okay, this would be a retrofit into another panel. So the display was mounted in the panel, and that's what it looks like from the back side. And then they mounted the AFR over here on the side on a piece of DIN rail. This would be a really typical aftermarket install. We also make a box that mounts on the side of the panel, and we call it an outdoor enclosure. If you don't have room to mount it in the panel, we have an enclosure to mount it out on the side of the panel or on its own separate mounting bracket. O2 sensors. A lot of talk about O2 sensors. Typically, this is the O2 sensor we use for our narrowband O2 sensor. It's an NTK. Very simple. It's a 4-wire heated O2 sensor. Interesting thing about O2 sensor. Let's go through the O2 sensors. A narrowband oxygen sensors. Okay, the sensor does not actually measure oxygen concentration, but rather the amount of oxygen needed to completely oxidize any remaining combustibles in the exhaust gas. A rich mixture causes an oxygen demand. This demand causes a voltage to build up due to the transportation of oxygen ions through the sensor layer. A lean mixture causes a low voltage since there is an oxygen excess. So, long and short is we're going to have more voltage coming from this narrowband O2 sensor the richer the engine gets. The more oxygen you have, the lower the voltage is going to be. Let's look at this. Lambda, we've covered this in the previous session, but lambda is the air-fuel ratio, the actual, so what the engine is running at for air-fuel ratio over the stoichiometric or the perfect burn, what science says that should be running at. And the difference will equal lambda. A narrowband is used for typically a lambda less than 1. A wideband O2 sensor is used for a lambda greater than 1. Lambda is the actual or operating air-fuel ratio divided by the stoichiometric or perfect combustion air-fuel ratio. A lambda of 1 is perfect combustion. Lambda greater than 1 is lean. A lambda less than 1 is rich. Example, if the stoichiometric air-fuel ratio was 10 to 1 and the engine was running at 15 to 1, lambda would be 1.5 or 15 over 10. Narrowband oxygen sensors, the part number is a 13009, 4-wire heated. Okay, pretty typical. Again, same one we've been using. All right, so when we look at this oxygen sensor, how in the heck does an oxygen sensor work, and what are the wires for on the oxygen sensor? We'll try to do this pretty simple explanation. This is more for field use and more for field explanation. Okay, so we have these two white wires right here. Okay, these two wires are 12 volt. Okay, and they're a PWM signal. And we do that, we bump that current in a square wave, and the amount of heat we need is determined, by the resistance. But to warm that up, we only turn it on for a short period of time, and we turn it back on, and then turn it back on and back off, back on, back off. And the more heat we need, the longer we leave it on. The less heat we need, the shorter time that it's left on. Again, that's 12 volt. There's no common ground, so they're not polarity sensitive on those two wires. Okay? Now, we've got a black wire and we've got a gray wire. The black wire is a signal wire. Okay? And so that wire is going to put out from 0 to 1,000 millivolts. Okay? And potentially 0 millivolts. So let's imagine we have this in the exhaust stream. Exhaust gases are going past this. One of the things that this has to do is it has to get heated up. It's no different than a little catalytic converter. Okay? It has zirconium and platinum. Okay? And this together, that cell in there is called a Nernst cell. N-E-R-N-S-T, Nernst cell. Okay? So basically, we have current coming out. Just like when the catalyst was working and we have the electron discharge, the more raw fuel or unburned hydrocarbons we have going across there, the more our current is coming off of here. And typically the most you could ever develop is 1 volt or 1,000 millivolts. On a typical rich burn engine, we're going to be running somewhere between 7 and 800, so let's imagine 750 millivolts is our target value. Okay? We also have to have this hot. The heater helps us warm up quicker, but it really keeps us stable as well. There's a heating element around this Nernst cell that's tied to these two wires. Okay? So as this warms up and as the fuel mixture gets richer, the number goes up. And as it gets leaner, the millivolt output goes down. So what we do is we pick a point where our catalytic converter is working the best when we're using an emissions analyzer, and then we look at the millivolt reading from this O2 sensor. And that reading we now will call our target. It's also referred to as a set point. Okay? Now, as the engine gets richer, let's say that the number went to 800. All we do is close the valve going to the carburetor, and it drops that number back down. We lean it down. If the number were to drop down to 800, we would open the, 700, we would open the valve and bring the number back up to 750 millivolts. So 750 in this particular engine would be our target. Once we get down into really low numbers, say below 400, below 300, it is no longer linear. It's not accurate at all anymore. These numbers are nothing that you would want to rely on. All you know at that point is that the engine is really lean. There's not enough unburned hydrocarbon in the exhaust. It's not rich enough for this little catalyst to have enough electrons discharged to it to produce that millivolt reading. Very simple. It's just a little catalyst. Anything that damages a catalytic converter damages an O2 sensor. One of the things you don't want to do is you don't want to get anti-seize on the tip of this when you're putting it in. If you do, they typically fail pretty rapidly, if not instantly, as soon as they warm up. Okay, this is a class 1 div 2 narrowband oxygen sensor. Has a sealed plug on it. Okay, another look at it. Your O2 sensors, you always want to install them as close to the engine as possible. The farther you get in the exhaust stream, the bigger the control loop is and the less stable your system becomes. So we usually like to put them right here. This happens to be a little 3306 turbocharged Caterpillar, and there's a boss that's on that elbow, and it's either going to have pipe thread in it or there's no thread in it at all, and we drill them out and tap them to 18 millimeter. Okay, and our post-catalyst O2 sensor is always going to be in the outlet nipple of the exhaust. This was in a make-ready shop, and so we don't have the rest of the tailpipe on this one, but it's always going to be in the outlet nipple. And that's so that we get a good homogeneous mixture of our exhaust gases and get a concentration. If you mount them on the outer wall, we've seen people do that. They'll weld an 18 millimeter boss on the outside. That shell doesn't have very good exchange of the exhaust gases. It doesn't do very good sampling out on the shell. The gases are somewhat stagnant on the shell of the housing. Okay, again, this is a picture we showed previously. This reason for this is do not put the O2 sensors up here. There's cases where you can't help it and you just have to do it, but this was not a case. This could have been installed down here. Again, this galvanized from this will make this fail. This leaking, we'll see oxygen and it'll continually richen the engine up as the exhaust leaks through here. Okay, when you put an oxygen sensor in and you have any joints in your pipe or not, you always have to be careful that you're not drawing air in. This would be incorrect installation here. A correct installation would be this way so that you're not drawing your pre-pipe should always be going over. The other thing is this should always be welded. Never use a clamp. Okay, never mount an O2 sensor below horizon. Always have the O2 sensor on a horizon or above. In other words, this should have been in the side up here with the O2 sensor coming out this direction versus vertical. This particular unit was on an offshore platform and it had a lot of exhaust pipe up above it, and when they start the unit the water would condensate and come down and ruin the O2 sensor almost every time they started the engine. The only fix to this, or the fix that we did on it, was drill a hole in the side and tap it to 18 millimeter and put it here. This happens to be a Waukesha, and Waukesha put that 18 millimeter port there from the factory. I don't know why. Okay, so here's another slide telling you how a catalyst works and what the voltage is on the O2 sensor. Okay, so the engine emissions going across the catalyst. Here's the top slide, or the top graph, is no catalyst at all. This is just normal emissions. You lean the engine out, the NOx get high, and the hydrocarbons go down, and the CO gets low. You richen the engine up, CO goes high, hydrocarbons go up, and the NOx goes down. Pretty straightforward. On this one, this is showing what happens with a catalytic converter. Your emissions drop. If you continue to lean out, you don't reduce your NOx, and your NOx numbers will be high. But in that same environment, this is what we're showing, the lambda voltage or O2 sensor voltage. It's not linear at all. It's called a narrowband sensor for a reason. It's really only accurate, this is very tight window, 0.975 to 1. If you get over a lambda of 1, the voltage falls off drastically and is not accurate at all. If you get a lambda of 1.025, which is a very, very narrow window, that narrowband sensor is not functioning at all. Okay. Here's another look at a wideband O2 sensor, or a look, not another look. This is a wideband O2 sensor that we use for our wideband systems. Okay. This is just an example of the difference between a wideband and a narrowband. If we look at this, the narrowband is this blue window right here, turquoise window. That's all the bigger it is, 0.97, 0.957 to 1, a lambda of 1.025, very, very tight window. But the reason they work so well is that's the same window that a catalytic converter functions in. If you were able to read down here with a narrowband, it wouldn't do you any good because the catalyst isn't working either. In the same token, if you were this much leaner, you wouldn't be able to read the numbers. The the O2 sensor would not perform, wouldn't give you any readings at all, but the catalyst would not be working either. It's a great combination for a rich burn engine because the O2 sensor is truly a small catalyst. Again, it does not measure oxygen, but rather the amount of oxygen needed to consume any remaining combustibles in the exhaust. So it's the same as a small catalyst. Very, very small window. Again, anything outside of this window, a three-way catalyst is not working. But you can see the range on a wideband O2 sensor is much greater and much more linear. Here, this slide showing the voltage drop on a narrow band versus the voltage reading, or the lambda reading, excuse me, on a wideband sensor. Much bigger window for the wideband, but the narrow band is a much more robust sensor, will survive a much rougher environment than, or hostile environment, than the wideband sensor. The wideband sensor is not near as robust. This is a remote mounted O2 sensor standoff. We would use this like we showed earlier, or we're showing you earlier, with the Waukesha 7044s. They work great in the wide pipe, but if you don't have that option, you can use a remote mounted O2 sensor. I strongly recommend doing whatever you can to locate them in the wide pipe, whether it be drilling or otherwise, and tapping in the Y pipe between the turbos versus using a standoff. The standoff is always the last resort. Okay, this is an installation on a 7042 with remote mounted O2 sensors. This particular picture was taken not because of the remote mounted O2 sensors, but because of the amount of anti-seize. These folks were destroying O2 sensors at a pretty high rate, and was discovered the amount of anti-seize they were using was damaging the O2 sensors. Again, here's that picture of the high temperature. Digital power valves, that's our next topic that we're going to cover. The digital power valves, we manufacture a few different styles, mainly the two inline valves. This would be 1.5 inch inline, and this one would be 1/2 inch inline. 3/4 are probably one of our most popular. Okay, a digital power valve features the Delrin Pinel valve homes to open. In other words, you can determine where you want that valve to be at startup. You can change the setting in it, and every time the unit thinks the engine stopped running and the AFR is still powered up, it always returns to that home position. It's got a user-definable startup set point. Again, you can determine where you want to set that. You can run the power valve from the controller itself. You can open and close that valve manually from touching the screen and the input on the screen. It's a rugged stepper motor. It's been around for years and years. Very, very little problem with that stepper motor. Installing the power valve, you want to size the valve correctly to the engine and its application. Having the incorrect valve will lead to poor performance and poor control range on the AFR itself. Install as close to the fuel mixer as possible. You don't want much distance between this valve and the carburetor itself, or the fuel mixer. Getting any more than about 6 inches away, the window of control gets smaller and smaller. By the time you're 12 inches away from the carburetor, there's really no use for the digital power valve at that point in time. The window is so small, you'll be forever trying to override manually. Install it so the condensate runs away from the motor. So the motor should always be pointed upward or always above horizon, at horizon or higher, so any condensate runs away from the motor. This would be a typical installation on a 3306 naturally aspirated engine. You have a tight 90 here. That's about as much distance as we want between the mixer and the digital power valve. Don't mount this down by the regulator or farther away. Again, by the time you get around this corner and try to mount it in here anywhere, you're really defeating the purpose of an air-fuel ratio controller. How does a stepper motor work? A stepper motor doesn't have an armature like a normal motor has. A stepper motor gets its positive and negative from the stepper driver within the controller itself. And the stepper driver will determine how far it steps and how far it moves. The farther it is away from the target set point on the O2, the faster the stepper motor is going to go. The closer it is, the slower the stepper motor is going to go. Okay, and we have from 0 to 500 steps, and each time it makes a change in the positive and negative on the fields, the stepper motor moves one step. To back that up, you change the polarity, it goes the other direction. It's called step logic. Here's a 1/2 inch power valve. There's an 1.5 inch power valve, very common valve. Dresser valve, another very common valve. This has 1.5 inch on one side and dresser coupling on the other side. Almost always used in a Caterpillar application, but can be used in any application. Just it was truly built for the Caterpillar units. Okay, here's an 1.25 inch on a 398 Caterpillar. You want that power valve as close to the mixer as possible. Don't get them down here too far away, or if you're not running hose and you're running piping. We see most commonly problem with this is mounted too far from the mixer. Closer it is to the mixer, the better control you're going to have. This would be a common installation for a 600D, so this would be a 3516, a CG137 application. Also some Waukesha GL versions would have the 600D on them. But you always want to use this bushing, which is a 2.5 by 1.5 inch, and put the power valve directly into that bushing. Don't get distance on these bigger carburetors. It's absolutely imperative that you mount these directly to the carburetor. Okay. How does a carburetor work? It's the next section. How are we going to adjust the fuel and set this unit up? Okay, this is a standard IMCO 200 carburetor. Okay, you see a lot of these out here. There's 600 vari-fuel carburetors. There's a difference in 600 vari-fuels. Some of them had a wear sleeve in here, and this particular one does not have the wear sleeve in it. But the advantage to these is you can change out this gas valve and you can change out the gas jet. And it's no different than jetting any carburetor. You set it according to how rich or lean your fuel is and what you're trying to run the engine at, what your performance you're wanting out of that engine. How much air is flowing through the carburetor and how much fuel you need going in is going to determine what gas valve and what jet size you use. Okay, so this is a vari-fuel 1 and this is a vari-fuel 3. The difference is the wear bushings in the carburetor. It's a rebuildable carburetor. Some of the earlier versions, Caterpillar on their 3516s, they installed a 7 Edwards 1659 washer. That washer went in place of this washer right here, and what it did is space that bullet out, and it resolved some of the starting issues. You can see in the vari-fuel you can also change the inlet gas cones coming in. There's different sizes, one for natural gas, one for digester gas, and you can see all the different gas jets that you can put in and all the different gas valves you can put in. This is only a portion of them that they're showing in this exploded view. There's 3 different springs that go in the different IMCO carburetors. One for downdraft application, one for updraft application, and one for side draft. And they're S2 and S231-1 and S232-3. So downdraft, updraft, and side draft, they're also identified with different colors. You can go to the book and find in the IMCO book, and you can find which jet you should be using and which gas valve you should be using. And these are all kit numbers where you get the jet and the valve, and it depends upon what you're running that with. Like this one is a CKV-62 enrichment for an AFRC for a catalyst with a lambda 1.1 to 1.3. So that would obviously be something leaner than a ridge burn. Okay, so just the different jets you can put in. You always want to make sure those carburetors are set up correctly. Look at the different springs that are used in here. You have the downdraft, side draft, and updraft, and then this is a custom for a turbocharge. This blue one is for a Waukesha. A little look at the difference in the jets. The jets, you can see the difference in the bore sizes. These three are all the same bore size. This one has a smaller bore size, but if we get a cross-section view of that, you're going to see the difference in the gas valves. There's a big difference in gas valves. Always have to make sure you have the right valve for the right fuel and the right load. Makes a difference in how well they start and how well they pull the load. Again, more of them in a cross-sectional view. When you see valves, jets and valves that are covered in this varnish, usually means the rest of the carburetor is going to be very sticky as well. You want to keep that from happening. This is just simply gas is what's doing this. It's deposits from their fuel gas that they have. Okay, worn out mixers. This one is worn out down in here. You can see this has come completely separated on this very fuel. This was on a KT or Cummins. KTA 19 is what this came off of. It was a side draft carburetor, and it becomes so worn and loose that this was flopping around and wouldn't align. Was a very hard starting unit and impossible to maintain emissions. It's just super imperative that carburetors and engines are in good condition for a unit to maintain emissions. Okay, again, a view at how worn out this carburetor is, and all the debris and deposits that are on this will tell me that it's going to be very sticky and very sluggish. Okay, let's set up a fuel system for a natural gas, non-turbocharged or naturally aspirated unit. First, you want to start out, you want to open your stepper motor up. Let's take that. Our range on the stepper motor is 500 steps to 0 steps. 0 is closed, 500 is open. Okay, we're going to put that valve about halfway at 250 steps. Okay, then we're going to go down here and we're going to adjust our fuel pressure. Now, the other thing is the regulator is designed to maintain fuel pressure on fuel that's flowing. Okay, so you want to start your engine and idle it is the most common way to set your fuel pressure and the most accurate way to set it, excuse me. This is a little Joe. So this little Joe, we're going to adjust the pressure on this based upon what this regulator range is set. If the max is 25, which would be common for a naturally aspirated small horsepower engine, we would set our fuel pressure coming out of this regulator, the little Joe, at 12.5 pounds. Okay, that's middle of the range for the spring that's in this regulator. Okay, 25 would be max, 0 would be minimum, and so 12.5 pounds would be the max inlet, or where we'd start, excuse me, the starting point. Okay, so we'd start at this point. Now the next thing is going to most carburetors, you're not going to want any more than 5 inches of water column. Okay, so you would take this cap off and you would adjust it with the engine idling so that you had 5 inches of water column. Now at this point, you've got it set, you're running at 5 inches of water column pressure going into the digital power valve. You also want to look at this manual power valve here. Typically we'll set that at 50% to start off with. We don't adjust this again until we know where this is going to run, where the digital power valve will run when we're in the control cycle or control status. Okay. Now, once you get that set to 5 inches of water column, now you start putting a load on the engine. You want to measure this. And when you're measuring fuel pressure, you always want to measure, here's your water manometer, you always want to measure between the pre-side of the carburetor and the fuel side of the carburetor. That's your air over fuel. And you want that fuel pressure to maintain that 5 inches of water column. One of the things you want to do, if you start putting a load on the engine and the fuel pressure would drop, you started loading the engine and now our fuel pressure dropped to say 2 inches of water column. That means we're not supplying enough fuel through this regulator, this orifice in this regulator. Now, we've already set this ounce regulator to 5 inches. Don't go back and adjust that again. This is where most guys make their mistake. They go back and adjust that after the engine's loaded. The problem with that is when the engine's not loaded anymore, this pressure will go up too high, and anytime we get over 7 inches of water column, this carburetor will start to act like it's leaking fuel into the system. And what it does is it picks up on the bullet on the diaphragm. Right in here, picks up on this, and the gas starts to leak into the engine. It'd be very similar to a gasoline engine that had a bad float in it. Okay, so if we need more fuel, you always go to the little Joe and increase the pressure. If you reach 25 pounds, that may be the max on this regulator. You always want to read the data tag up here on the regulator. Okay, so once you reach the max for that regulator, that means, and you're not able to maintain 5 inches of water column under a load, that means the orifice in this regulator is not big enough. That means you need to increase the orifice size. Okay? Better to have too large of an orifice here for nice gentle fuel delivery than too small of an orifice and have this pressure set too high. It makes the carburetor very erratic. Okay, what is inches of water column? Well, we use a water manometer. This would be a true water manometer here. And once we push down by 2 inches, that means we've got 4 inches of differential here. This one is showing 4 inches of water column. It's not very much pressure. 5 inches is typically max for most naturally aspirated engines. Okay, and here's what they look like. Here's a electronic one on the left, and here's a slack tube, a Dwyer slack tube on the right. They both have their purpose. The great thing about the electronic is they're always readily available. They're very accurate. The one thing about them is they're slow. If you're trying to find worn regulators, that will be a problem because it'll jump around and not show it on the display. If you use a slack tube, the advantage to a slack tube is you will see worn regulators or anything that's erratic, because that's water in this manometer will be bouncing and telling you something's wrong, versus the electronic one, you don't always see that bounce. The advantage is there's no mess with this guy, and with the slack tube, every time you put them away you got to drain them out and clean them, or they'll be all over in the box or in your truck. Okay, just a little notation here. You can go to the book, like on a Very Fuel 600, and you get all the specs. And one of the specs I want to show you here is so many guys or gals, whatever, service techs, will set the pressure much too high when the engine's loaded and then they don't start. These mixers are not supposed to have over 5 inches of water column. There isn't a normal mixer out there. There's a few brands that maybe go a little higher. There's one that's built for an air-fuel ratio controller in it that's higher. But as a rule, carburetors are not supposed to have more than 5 inches of water column on the inlet of that carburetor. They get very difficult starting. Okay, to tell you how light water column is, 1 psi is 27.6 inches of water, or 1 psi equals, or excuse me, 1 inch of mercury is 13.6 inches of water, and 1 ounce is 1.7 inches of water. Always make sure if you're using a gauge, you're using inches of water column. The ratio isn't very accurate. It'll be really hard to read on an ounce gauge, say 5 inches of water column. You're only going to be a little over 3 ounces, which is difficult to read on the gauge. Okay, high pressure fuel systems. What is a high pressure fuel system? A high pressure fuel system typically has a turbo boost going into the mixer, and then this would be going to the engine intake manifold. The part we're concerned about on this is what should our fuel pressure be. This is where we always want to check fuel over air. Okay, so we would have a test port in here somewhere, and we'd have a test port on this housing, and we would measure our differential between the two. Okay, and we always want to measure this delta P between the manifold and the fuel pressure. The reason being, we always have to maintain 5 inches fuel over air. That's the only way that fuel is going to get in the carburetor, is if it's 5 inches above. So that being said, if we're running something with 15 pounds of boost, our actual fuel pressure going into this is going to be 15 pounds plus 5 inches of water column. And that 5 inches of water column is adjusted right here in the regulator when you adjust the spring. Again, you set that at low load or no load with the engine idling, and if you need more fuel, you either have to change the orifice or you increase this no more than the max of what this regulator is rated at. Okay, so typically in this situation, that regulator is going to be set for 50 pounds max. Okay, so we would never want to have this set higher than 50 pounds, or we could have a regulator explosion. We only have to overcome 15 pounds of boost and any losses we have by restrictions in orifices. So this is a high pressure fuel system. Your fuel supply is always going to have to be higher than the boost pressure. So at minimum, it's probably going to be about 25 pounds to 50 pounds coming into this to account for any losses. Low pressure fuel system works quite a bit different. Low pressure fuel system, we're blowing the boost directly into the engine. Okay, but the gas is being mixed on the low pressure side of the turbo. So this is going to go into a negative inches of water column. Okay. Now on this is really common. You'll see this on Caterpillar gensets. You'll see this on 3516 Caterpillars with twin carburetors on them or dual carburetors. You'll see this on CG 137s, -8s, and -12s. Low pressure fuel systems were originally designed to operate on utility natural gas, where they had a low pressure rating for a building, say a standby generator for a building or apartment complex or office building would be supplied with utility natural gas. And that utility natural gas is usually between 2 to 4 psi coming into this. So the problem with that is you would never be able to overcome the boost pressure on a high pressure fuel system. So they developed a low pressure fuel system. And in our industry, they use this for low suction pressure units, or units that have very low wellhead pressure so they can get them started. The advantage to this is you don't need very much fuel pressure at all. Now what happens is, as you start to load that engine and the boost pressure comes up, the restriction comes across this. Now we're going to set this fuel over air. Again, here's our water manometer, and we're going to tie this to the fuel, and we're going to tie this to the air side. And the restrictions of the air cleaner and just the velocity of the air going through there, we may start out at a light load at 5 inches of water column. But when we get under a heavy load, we need less fuel. The regulator actually backs off. And there's a balance line that goes between this regulator and the inlet on the mixer. And what that does is this, as this starts to pull and there's a restriction and it goes into a negative, it picks up on the diaphragm of the regulator and backs the fuel pressure down. So you might be idling at 5 inches or carrying a light load at 5 inches and running under full load, and maybe only be at 1 or 2 inches of water column full load. Okay, so that's the difference between a high pressure and a low pressure fuel system, is how much do we need to get the fuel pressure into the carburetor. That's the difference. We're not trying to overcome boost. Now regulators. This is a common regulator used with a low pressure fuel system. This is called a 133 zero governor. This is a Fisher. And you'll see these on the low pressure fuel systems on Caterpillars and other engines as well. I'm most used to the Caterpillar engine. So this requires low pressure going into the regulator, or zero governor, and this has a very large orifice in it, a couple inches across. So that doesn't have to open very far to let a lot of fuel going to the mixer. Okay, and this also doesn't open until the mixer sees a negative pressure. Okay, too many guys try to overpressure these and it makes it very unstable. I see a lot of it on the CGs where they're trying to run 10 to 20 psi to carry a load, and then they can't start the unit. Well, that's because that pressure is opening this seat. Weak links on this regulator are this right here. This is always exposed to the fuel gas, the shaft is, and when it's open, when that is open, the debris and the varnish build up on this shaft, and then it can't close correctly, and then you have a very difficult time starting them. I've seen these shafts wedged in there where we had to take the regulator apart and drive that shaft out of there. Usually not worn out, they just get debris and varnish built up on that shaft. Very common regulator here, 200 series or 300 series, either one. Good stable regulator. They tend to wear out a little faster than some other regulators. The wear points are right here. You'll see that worn out right there, and as that wears out, the regulator will become less and less stable because that doesn't slide as it goes up and down to regulate the fuel. The other places they wear out is the seat gets bad. You can replace the seat if they're leaking, and the bushings get worn out in here. You can buy rebuild kits for these. Typically, you'll replace these regulators every couple of years, or say less than 20,000 hours. You'll want to go in and either rebuild or replace these regulators. Very common regulator. Okay, this is just a sheet showing the different springs that you put in for your different pressures. We're going to run, typically, we're going to run this red spring in the 200 regulators. And that's your 3.5 to 6.5 inches. Remember, we said 5 inches was where we always want to be. 5 to 9 inch, that's a little bit too high. That's the black spring. You'll have trouble starting on certain engines if you install that spring. Red spring is usually the safest spring to put in. Different orifices. If you're having difficulties with the unit being loaded and you're not running rich enough to meet your emissions, the engine's leaning out too far, you can always install a bigger orifice. There's several different sizes available depending upon the regulator that you're using. Y600, very popular regulator for Caterpillar and other applications. Very robust, very reliable regulator. One of the things that's not good is the way this regulator often gets mounted. It gets mounted in the vertical position and moisture tends to build up into it. And then the regulator hangs up and doesn't control correctly. We want to take them apart and clean them and get the moisture out of them. Little Joe's, don't see many issues with Little Joe's at all. Very robust regulator, very stable, very strong regulator. Carburetors, IMCO 200 carburetor, one of the things you want to look for is wear points. They wear on these flutes in here. There'll be a little shoulder worn in where the diaphragm and air gas valve assembly have been rubbing. They'll wear off on these. This one will be worn the most because the flow of the air is this direction and pushes the diaphragm over. Always check and see, put your finger in there and see if you can see a little lip, feel a little lip in there. If there is, throw the carburetor away. There's no repairing for that. And too many guys will fight them. They get hard starting. They have troubles meeting emissions because the emissions are erratic as it jumps over the shoulder that's worn in there. The wear spot is normally right where the engine's carrying the load most of the time, and any deviation from that makes it challenging to meet emissions. This is a 600D, 600T, and again, these flutes in here are going to be your wear points. And then inside this air gas valve assembly, you'll get notches worn. Always make sure your carburetor's in good condition. This is a typical diaphragm out of an IMCO carburetor. If this was worn out, you'd see notches worn down in here in 4 different spots. And if you see those, just replace it. Typically the carburetor's worn out as well. The other thing is this gasket is in really bad shape around this one. If that doesn't seal, the diaphragm doesn't react correctly. This will conclude today's session. Thanks for watching. I hope we provided you some value today, and we'll catch you next time. Thanks and have a great day.